Hi everyone, welcome back to the channel. In this video, we shall try to learn about two important things. One is the Werner's theory of coordination compounds, and number two, the meaning and calculation of effective atomic number of the given complex compound. So now we shall directly enter into the concept. We know that when certain definite number of ligands approaches the central metal ion, each ligand will donate certain fixed number of electron pairs to the central metal ion and thereby developing a coordinate bond between the central metal ion and the ligands. So in order to explain the formation as well as once the ligands attach it to the central metal ion, how the ligands will orient in the space, so that what kind of geometry the formed complex compounds do exhibit. In order to explain all these things, in the year of 1823, scientist by name Alfred Werner proposed a very useful theory which is regarded as Werner's theory of coordination compounds. And in order to honor his work on coordination compounds, Werner was awarded with Nobel Prize for the first time in the field of coordination chemistry. And because of that reason, Werner is actually regarded as father of the coordination chemistry. So this is the first honor given to a scientist in the field of coordination compounds. So now we shall look over what he actually proposed in order to explain the formation as well as the geometry of the formed coordination compounds. So that we shall see under the postulates of his theory, that is postulates of Werner's theory. So the postulate number one is, according to Alfred Werner, the central metal ion which is present in a given complex compound do possess two kinds of valencies. Each metal ion will possess two kinds of valencies which are called as, one is primary valency and obviously the second type of valency is secondary valency. So this is the first postulate proposed by Alfred Werner under his theory, according to which the central metal ion of the given complex compound do possess two types of valencies, that is primary valency and secondary valency. And among this primary and secondary valency, this primary valency is ionizable one, and this primary valency is not having any directional properties. That means the primary valency is non-directional. And if you come to the case of secondary valency of the central metal ion, unlike primary valency, the secondary valency of the central metal ion is non-ionizable. As well, the secondary valency is having directional properties, means it can be oriented towards a particular way, particular direction in three-dimensional space. So that is about primary and secondary valency. As we said, primary valency is ionizable, that means it can be changed. And secondary valency is non-ionizable, it will be fixed. Okay, so that is according to primary and secondary valency. Now the same thing, the primary valency of the central metal ion, the primary valency of the central metal ion is corresponding to the oxidation state of the central metal ion. Primary valency of the central metal ion corresponds to oxidation state, and the secondary valency of the central metal ion corresponds to the coordination number of the given central metal ion. Secondary valency corresponds to coordination number of the central metal ion, that is CMI. And we know that primary valency is in correspondence with oxidation state, means a metal ion do possess positive state, positive oxidation state. So by considering this particular concept, Werner said that the primary valency of the central metal ion will be satisfied. The primary valency of the central metal ion will be always satisfied by the negatively charged ions. And in the same way, the secondary valency of the central metal ion will be satisfied by either negative ions or it may be neutral molecules. So both the components can satisfy the secondary valency of the central metal ion. So we can do the comparison. Here we are telling the primary valency will be satisfied by the negative ion, since the primary valency is nothing but oxidation state of the central metal ion which is positively charged. In order to satisfy that positive charge, the negatively charged ions are required. And secondary valency means the coordination number, that means the ligands. So we know that either negative ions or neutral molecules, both of them can behave as ligands. That's what we are telling, coordination number. That means the total number of coordinate bonds forming by the ligands with the central metal ion. This is the information we can get from primary and secondary valencies. And after this, the most important thing said under the Werners theory is the secondary valency of the central metal ion. That means the coordination number of that central metal ion cannot be varied. That means for each and every central metal ion or central metal atom which is forming the complex compound, the secondary valency of the central metal atom is always fixed one. There will be no variation in the coordination number. If you consider a particular central metal atom or central metal ion, its coordination number will be always fixed. Say for example, cobalt, its secondary valency is fixed, that is 6. And if you go with the nickel, its coordination number will be 4. And if you go with central metal ion chromium, its coordination number is fixed, that is 6. And if you go with the central metal ion Ag, its coordination number is always fixed, that is 2. Like this, the secondary valency of each and every central metal ion is always fixed one. And lastly, we said the secondary valencies are having directional properties. The secondary valencies are having directional properties means they can orient in a proper angle in three-dimensional space. So when the secondary valencies are directed towards a fixed position in three-dimensional space, and that will result to give the definite geometry or the structure for the given coordination compound. That means the definite geometry possessing by a coordination compound will be explaining by the orientation of secondary valencies in space. So depending upon how the secondary valencies, that means the ligands, have been oriented in three-dimensional space, that gives a definite geometry for a given coordination compound. Say, for example, as we said, the coordination number can be 2, can be 6, can be 4. So here Werner have considered two important coordination numbers, the regular coordination number, that is 4 and 6. If the coordination number, that means the secondary valency of the coordination compound, I mean to say the central metal ion, is 6, then the 6 ligands will be there, the 6 ligating atoms which are present around the central metal ion will be present at all the 6 vertices of the octahedron. Therefore, the 6 coordination numbered complex compounds do exhibit octahedral geometry. Octahedral geometry. And if the coordination number, that means the secondary valency of a central metal ion, is equals to 4, then here you will be getting two possibilities, that is the complex compound either may have tetrahedral geometry or it may have the square planar geometry. So in this way, Werner put forward to explain the orientation of the ligands around the central metal ion and thereby predicting the geometry of the given complex compound, as well as a bit about the formation of the complex compounds just by approachment of ligands towards the central metal ion and forming the coordinate bonds with it. And that's the whole and sole thing about the Werners theory. And now we shall consider one or two examples in order to apply the postulates of this Werners theory, and so as to explain the exact molecular formulae and exact geometry of the given coordination compound. Let us consider the example of a cobalt complex, so which is having the constitutional formulae CO, Cl3, 5NH3. So this is the constitutional formula of the complex compound, and here the central metal ion is cobalt, and for cobalt the primary valency is 3. That means the cobalt is existing in +3 oxidation state, and as we already said, the secondary valency of each and every central metal ion is always fixed, and for cobalt the secondary valency is fixed, and that is equals to 6. But here for cobalt totally we are having 5 plus 3, 8 constitutional components. So now here we are supposed to decide which one is acting as ligand and which one is acting as the ionic sphere. I mean, is there any presence of ionic sphere, or whether all are acting as ligands? But it is not possible to consider all the constituents as ligands, because totally we are having 5 amine ligands and 3 chloroligands. So totally we are having 8, but the secondary valency of cobalt is fixed and it is equals to 6. So among these things there is an ionic sphere also. That means we have to find out the exact molecular formulae of this particular complex compound also. Then only giving a proper IUPAC name for the given coordination compound is possible. So now we shall trace out the exact molecular formulae by considering this constitutional formulae. And now, according to the principles of or the postulates of Werners theory, the primary valency of the central metal ion will be satisfied by the negative ions, and the secondary valency of the central metal ion is satisfied by either neutral molecules or negatively charged ions. So here NH3, we already said it is a neutral monodentate ligand, and chloro, it is a anionic monodentate ligand. So from the last postulate of Werners theory, we can say that when the secondary valency is equals to 6, the possible geometry is octahedra. So cobalt will be there at the center. So octahedra 1, 2, 3, 4, 5 and 6. There are 6 vertices. So the bonding between ligands and the central metal ion is coordinate. So first we shall consider the neutral molecules which can behave as a secondary valency. So NH3, there are 5 NH3 molecules. So 2, 3, 4, 5. So we have written all the 5 NH3 molecules which are satisfying the secondary valency. But the one more vertices have been left. So at this position we have 3 chlorines. So only one chlorine can fit over here. But still we have 2 more. That means the remaining 2 are not acting as ligand. That means they are not satisfying the secondary valency. They can satisfy only primary valency. So let me show in this way with the dotted lines. So here one Cl and here one Cl. So here I have shown 2 kinds of bonds, solid lines and dotted lines. This solid lines accounts for the secondary valency and this dotted lines accounts for primary valency. But the primary valency of the cobalt is 3. That means 3 positive charges. So we should have 3 negative charges, right? So 1, 2, 3. So this will also involve in balancing the primary valency of the central metal ion. So mean these 2 chloro molecules or chloro ions are satisfying only primary valency, but this chlorine is satisfying both primary as well as secondary valency. So now we shall frame up the formulae for this particular compound. So central metal ion is cobalt, and now we shall write only the ligands within the square bracket, that is in the form of coordination sphere. So central metal ion is cobalt and the ligands are 1, 2, 3, 4, 5. 5 NH3 molecules are acting as ligands, and among these 3 this is acting as ligand. So 5 plus 1, 6. Secondary valency is satisfied. And what about these 2? These 2 are simply satisfying the primary valency, and that will comes out. That means whichever the constituents of the complex compound which is present extra other than the components that are completely satisfying the secondary valencies and indicating only primary valency, the constituents which are shown with only satisfying primary valency, that will be present outside the coordination sphere. So this is the complete formula for this particular complex compound of the cobalt. So now it is easier to give the IUPAC name for this particular compound. Here we cannot, but here we can easily say. So now for this the IUPAC name will be, so first we need to see the names of the ligands, because the coordination sphere is present in the form of cation and the ionic sphere is the chlorine. So first we should say for cation, and among this the ligands are supposed to be named. There are 5 amine ligands and 1 chloro ligand. So penta, amine, there is 1 chloro, and the central metal ion is cobalt, and the primary valency, that is oxidation state, is 3, and the ionic sphere is chloride. That is the IUPAC name of this complex compound. And we can notice that when you add, we said the coordination compounds are soluble in water, right? So we can add this particular complex compound into water, we will be getting the solution. But one question will comes into our mind. So here we have chlorine, that is halogens are there. So when the solution consisting of halogen is added up with aqueous solution of silver nitrate, we will be getting a white precipitate, right? So we can say, or we can ask, how many molecules of, or how many moles of silver chloride precipitate will be obtained when this is reacted with excess of AgNO3. So by looking over to this formula, it is not possible to say, but by considering this, we can say that the chlorine which is present inside the coordination sphere will not come out into the solution as a Cl minus, and the components which are present in the ionic sphere can enter into the solution in the form of Cl minus, and each Cl minus can interact with one AgNO3 molecule to form one AgCl. So here totally we have two Cl ions outside. So when this compound is treated with excess of aqueous AgNO3 solution, and this will give 2 moles of AgCl as a white precipitate. So by using Werner's theory, it is possible to predict the products which are forming when material is reacted with certain particular reagent. So like that, we shall consider one more example. This is the second exemplification. The constitutional formula is this one. Central metal ion is platinum. There are 4 chloromolecules and there are 3 amine molecules. Because I have not yet confirmed which components are actually acting as ligands, that's why I have used only molecules. Okay, so now in order to develop the exact molecular formula of this particular complex compound, we should know the exact primary and secondary valency of the central metal ion platinum. And for platinum, the primary valency is +4, that is 4, and secondary valency for the central metal ion platinum is fixed and it is equals to 6. So now we shall draw the possible geometry for this particular constant. So in order to find out the exact molecular formulae of this particular complex compound, now we shall draw the exact geometry of the molecule by looking over to its secondary valency. And here it is given the secondary valency of the central metal ion platinum is 6. So the possible geometry is octahedra. So platinum. So we shall draw the 6 vertices of the octahedra. So first the secondary valency. The secondary valency is supposed to satisfy by neutral molecules and also the negative ions. So first the neutral molecules. There are 3 NH3 molecules. So first ligand, second ligand and third ligand. So now the neutral molecules have been completely added into the 3 vertices of the octahedra, and still we have 4 chloro ions that has to be added now. This is 1, 2 and 3. So all the vertices is filled, but still we left out with 1 Cl. So when all the vertices are filled, we will be leaving that chlorine that can satisfy only the primary valency but not secondary valency. But now we shall go with the satisfaction of primary valency. So the primary valency of platinum is 4. So for satisfying these 4 positive charges of the platinum, there should be 4 negative charges. So 1 is already there. So second one, this can do the second, this will be the third, this will be the fourth. So by looking over to this particular structure, we can say among the 4 chloro components, 1 chlorine is satisfying only primary valency and 3 chlorines are satisfying both primary and secondary valency. So by looking over to this, now we shall try to frame the exact molecular formula for this constitution. So the central metal ion is platinum. And now we shall incorporate the ligands within the coordination sphere. So 1, 2, 3, there are 3 ammonia ligands, and solid line 1, 2, 3. So there are 3 chlorines which are acting as ligands. That's fine. So coordination number 6 is satisfied and we left out with 1 Cl. Since it is anion, it will be written over here. And this is the molecular formula for this particular compound. So now by knowing the molecular formula, it is possible and it is easier to say about the exact IUPAC name for this particular compound. So first we should say the cation. The coordination pair itself is acting as cation, and this is ionic pair. So first, in coordination pair, we should say the names of the ligands in alphabetical order. So there are 3 amine ligands. So triamine, and there are 3 chlorine ligands. So trichloro, triamine, trichloro. So all the ligands are finished. So now we have to say the name of central metal ion, platinum. Since the coordination pair is a cation, no need to say as platinate. So when the complex is an AN ion, then we should end the name of the central metal ion with the suffix ate. But here it is not the case. So we can retain the name of the central metal ion as it is. And the primary valency is 4. So we should written in the form of Roman number. At last we should say the ionic pair, that is chloride. So that is the IUPAC name of this particular compound. And here you can see once again the same condition. When this particular compound is treated with aqueous solution of AgNO3, the question, how many moles of AgCl precipitate will be formed? So in order to say that, by considering this constitutional formula, it is not possible to say. But if you go with this one, you can see inside the coordination pair there are 3 chlorines which cannot come out into solution in the form of Cl-, but this ionic pair can come into the solution as Cl-, so which can only react with aqueous AgNO3 to form AgCl. So here we get only 1 mole of AgCl precipitate. Right? So we shall give one more example at last for Werner's theory. So one more example for Werner's theory. The constitutional formula is CO Br3 3CO. So once again the complex of cobalt. So for cobalt, once again the primary valency is 3, that is +3, and secondary valency is 6. Right. So now we shall go with the vertices of the octahedron. So first we should go with the neutral molecules. So carbonyl ligands 1, 2, 3. So the 3 carbonyl ligands are acting as ligands, and now we have 3 more bromanes. So 1, 2, 3. So all these 3 are acting as ligands only. So secondary valency is completely satisfied and all the constitutional components have been accommodated at the 6 vertices of the octahedron. And now we shall go with primary valency. And the primary valency of the cobalt is +3. So in order to satisfy this 3 positive charges, there should be 3 negative charges around this cobalt. So here is 1 bromine. 1, 2, 3. So these 3 bromides are satisfying the primary valency of the cobalt. So by looking over to this, we can say in this complex the 3 bromoligands and 3 carbonyl ligands are satisfying the secondary valency, and these 3 bromines along with secondary valency, they are satisfying primary valency also. So we can frame the exact molecular formulae. CO, there are 3 carbonyl ligands and there are 3 bromine ligands. So secondary valency is completely satisfied, and there is no other thing which is satisfying only primary valency which can be written outside the coordination pair. So that this is the complete molecular formulae of the coordination compound. That means there is no ionic pair, there is only coordination pair. That means the coordination pair is a neutral one. But in the above 2 cases we observed it is a complex cation, but here we are getting only neutral compound. And now we shall see the IUPAC name for this one. So first, carbonyl starts with C, bromo starts with B. So first we should go with the alphabet B, that is tri, bromo, again tri, carbonyl, and the central metal ion is cobalt, and the oxidation state is 3. So that's about the IUPAC name of this particular compound. And once again, when you treat this material with aqueous solution of AgNO3, prediction. So when AgNO3 is treated with chloride ions, you will be getting a pale or curdy white precipitate. But when you are treating AgNO3 with bromide ions, you will be getting a pale yellow precipitate. So a question may be asked. So when this particular compound is treated with aqueous AgNO3, how many moles of pale yellow precipitate of AgBr can be formed? So if AgBr has to be formed, means in the solution it should come in the free state. I mean to say free Br minus ion. You can observe the complex structure. All the 3 bromide ions are acting as the ligands, and they are present inside the coordination sphere, which cannot come out into the solution in the form of Br minus. So no possibility of the formation of AgBr. So this will not form. So like this, we can predict the chemical reactivity of the compounds also by knowing the values of primary and secondary valency. So though this Werner's theory is useful in all this way, still it is having some limitation. That means Werner's theory is failed to explain the exact way of joining of or binding of ligands to the central metal ion. As well, we have seen at the last postulate of the Werner's theory, if the coordination number of the central metal ion is equals to 4, the possible geometry is either tetrahedral or square planar. So Werner's theory didn't give a proper explanation that whether a 4 coordinate system is tetrahedral or square planar. So in order to overcome all these things, some additional or modified or updated theories have been proposed, such as valence bond theory and crystal field theory. So for this instant, this is the whole and soul stuff about the Werner's theory. So now we shall discuss about one more important concept, that is effective atomic number. So now we shall go to the next topic, that is effective atomic number, simply abbreviated as EAN. So if you consider a coordination compound, in that coordination compound there will be a central metal ion, and it is surrounded by a definite number of, that to say a fixed number of ligands. And if you consider the electrons that are present in a central metal ion and the total number of electrons contributed by the ligands, if you have taken the arithmetic sum of the total number of electrons present in the central metal ion and the ligands, what the number of electrons you will get, that number is simply called as effective atomic number. That means the total number of electron possessing by a central metal ion, including its valence electrons and the electrons gained by the central metal ion from the surrounding ligands. That is called as effective atomic number. And one concept is why this concept of effective atomic number is arised. So in case of Werner's theory, we said each and every central metal ion will have a fixed secondary valency. That means the coordination number of the central metal ion will be fixed. So why it is fixed? In order to solve that doubt, this effective atomic number will give a much support for the Werner's theory. That means, so to a particular central metal ion, the ligands will be continuously added. That means we know that each and every ligand, that means each and every ligating atom can donate 2 electrons, that is 1 pair of electron to the central metal ion. So up to what that donation of electrons by the ligands will continue? That is, the addition of the ligands to the central metal ion will happen continuously until the central metal ion possess or attain the total number of electrons which will be equal to the number of electrons present in the next noble gas. So till that, the central metal ion will continuously receive the ligands. That means once the number of electrons of the nearby noble gas is filled by that particular central metal ion, then that particular complex will become stable and there is no more requirement of the electrons by the central metal ion. So it won't receive any ligands at all. Thereby we can say the secondary valency, that means the coordination number of the central metal ion will remain fixed. That is the support given for the Werner's theory on the basis of this effective atomic number. And now we shall see how we can calculate the value of the effective atomic number of a particular complex. In order to calculate the effective atomic number of the given coordination complex, we can use a very simplest molecular formulae, that is simple mathematical formulae, that is EAN is equals to Z minus X plus Y. So we can use the simple mathematical form in order to calculate the value of effective atomic number of a complex compound. Here Z is the atomic number of central metal ion and X is the oxidation state of the central metal ion. Y is total number of electrons donated from all the ligands surrounded the central metal ion. So by knowing these three values, we can easily calculate the value of effective atomic number. And now we shall consider some examples in order to calculate the effective atomic number. So first let me consider one simple example. Say CONH3 6 times with 3 positive charge, and here cobalt is the central metal ion which is existing in 3 plus oxidation state, and we know that the atomic number of cobalt is 27. So we can calculate the value of EAN. So EAN is equals to Z minus X plus Y. The value of Z, that is atomic number of cobalt, is 27 minus oxidation state is 3 plus there are 6 ligands and NH3 is a monodentate ligand. Each ligand can donate 2 electrons. So 6 into 2, 12. So when you calculate 27 plus 12 minus 3, you will be getting 36 electrons, which is the atomic number of krypton. So thereby we can say the complex is stable. And shall consider one more example. Shall consider one heteroleptic complex, PT NH3 thrice Cl3 with a positive charge. So here the platinum is in 4 plus oxidation state and the atomic number of platinum is 78. That is the value of Z. So now we shall calculate the value of EAN. So EAN is equals to Z, that is 78 minus oxidation state is 4 plus, so 3 plus 3 6, all are monodentate ligands, so 6 2s are 12. So 78 plus 12 minus 4 will be getting 86, which is the atomic number of radon. Once again a noble gas. So in both the cases we have considered the complex cations. So we shall consider one complex anion also. So example number 3, Cu Cn 4 times with a 4 minus. So here we have the complex anion, and here the central metal ion is copper, which is existing in +1 oxidation state. So for which we shall calculate the value of EAN, and copper atomic number is 29. So EAN. So EAN, the value of Z will be 29 minus oxidation state is 1 plus 4 cyanide ligands are there. So cyanide is a monodentate ligand. So 4 numbers are there. So 4 2s are 8. So 29 plus 8 minus 1. So once again, I am getting 36. Once again, which is the atomic number of krypton. So in this way, we can calculate the value of effective atomic number, and based on that, we can say whether a formed coordination complex is stable or unstable. But for this concept also, there are some exceptions. That means we have many stable complexes which are known to exist, which are not going to satisfy the EAN rule, but still they are stable. Though they are not satisfying the EAN rule, they are very much stable. If you consider one such example, CuNH3 4 times with the 2 plus charge. So here the copper is a central metal ion and it is in 2 plus oxidation state. So now we shall calculate the value of effective atomic number. So atomic number of the copper is 29 minus oxidation state is 2 plus 4 monodentate ligands are there. So 4 2s are 8. So 29 plus 8 minus 2, I am getting 35, which is short of 1 electron from the atomic number of krypton. So as per the EAN rule, it's not supposed to be stable, but still this complex is very much stable. The reasons are many. So that all those things we shall discuss in the upcoming topics. So and that's about the effective atomic number. So that's about today's in this video. So if you feel the video is worthy and useful, please like it, share it, and do subscribe to my channel and press the bell icon so that you will get the notification for any update in my channel. Thank you very much.